Hello, my name is Cathy Fang, and I'm an undergraduate at Carnegie Mellon University, majoring in mechanical engineering at HCI. Today I'd like to introduce Wireality, a warm multi-string haptic system that enables interactions with complex, tangible geometries in virtual reality. This work was done at a Feature Interfaces group at Human-Computer Interaction Institute at Carnegie Mellon in collaboration with Zhang, Matthew Dworman, and my advisor Chris Harrison. Today's VR systems, such as the Oculus Quest, as you see on the left, and HTC Vive, as you see on the right, use controllers for tracking the hands, capturing button input, and delivering basic haptic feedback through vibrations. The latter is insufficient to produce immersive physical interactions with virtual objects. More critically, large obstacles such as the walls, railings, and furniture, which are key elements in most VR worlds, are not simulated at all. This shortcoming has long been recognized, and researchers have looked into ways to bring rich haptic feedback to VR experiences and on different parts of the body. Closer to our work are VR haptic systems for the arm and hands. Researchers have rendered haptic illusions for grasp using mechanisms such as exoskeletons and pneumatics. Among them, strings offer a lightweight approach, allowing the main mechanism to be placed somewhere less cumbersome. Prior work has also attached strings directly to users' hands. Most related to our work are those that are self-contained and wearable. We set out to design a new haptic system that was, first of all, self-contained and mobile. This implied a worn system, which needed to be both lightweight and battery-powered. To simulate realistic interactions, specifically with heavy or fixed objects, we need a system that could provide large arresting forces for the forearm and hand while supporting complex geometry with low latency. We also aim for a low-cost design that could be mass-produced for under $50. Moving beyond prior work with a truly wearable and mobile implementation, we introduce Wireality, which delivers haptic feedback to the whole arm and each hand joint independently, that enables complex haptic interactions such as touching planar and curved surfaces, the wrapping of fingers around virtual railings and poles, as well as touching irregular objects and surfaces. Before I talk about how we made Wireality, I wanted to talk about the inspirations that led to the design. Our inspirations were objects that seem to have little connections to VR or haptics. The first one is these retractors, which you may have hooked a key or a badge to. We used a flat torsional spring inside to keep the strings taut and as the hand extends. The second inspiration is seat belts, which secure our body in place during a sudden stop. We borrow the same ratchet and paw design that allows one-directional free rotation to lock the hands in place. A combination of both inspirations, we created our first prototype. And we also experimented with a motor-based design which would afford more dynamic haptic effects compared to the fixed force feedback that is determined by the spring constant. However, we quickly noticed its downsides and chose the spring-based system. Because the motor is heavy, bulky, heats up quickly, and most importantly consumes a lot of power. For both of these iterations, we used a 10-turn potentiometer for tracking the finger distance from the module by counting the rotations of the reel. Ultimately, we replaced it with computer vision for higher accuracy. The final design of a Wireality module is responsible for limiting 1 degree of freedom on the hand, which is comprised of spring-loaded cables that we can programmatically lock with a ratchet gear and a solenoid-driven pawl. We were able to achieve a low-cost design made out of laser-cut acrylic and 3D printed housing, as well as commercial retractors and solenoids. Now let's take a closer look at a design. A high-tensional resolution can mitigate visual haptic mismatches. Since the pawl can only latch the gear at tooth boundaries, the resolution can be increased with a greater tooth count, but that also means the pitch depth will decrease, making it harder for the pawl to engage with the ratchet securely. After many iterations, we achieved a final resolution of 0.84 millimeters per tooth. We chose an 80-gram pull force retractor, suitable for removing slack at typical human movement speeds, while not being overly distracting. The retractor comes with a steel cable that is both strong and wear-resistant. We use a 12-volt push-pull solenoid that consumes 2.19 watts per actuation. With the ratchet design, the actuation is kept under 40 milliseconds, thus each locking event consumes merely 0.024 milliwatt-hour. Now let's look at how these components work in concert to minimize energy consumption while remaining fast and accurate. When the hand collides with a virtual object, our software triggers a solenoid to actuate, pushing a pawl into the ratchet, which locks the spool from further rotation, arresting the finger and ultimately the hand. Force exerted by the user on the string keeps the ratchet engaged, and thus the solenoid can be empowered after a brief interval. Only when the user withdraws their hand is the pawl released and the spring can retract any string slack. Let's look at this again without pausing. This is very energy efficient while offering very strong resistive forces. Our study shows it is also fast acting and spatially accurate. For our final implementation, we combine 7 modules together and attach strings to the 5 fingertips, the palm, and the wrist of the hand. With 7 modules acting together, Wireality can simulate a wide range of objects. As mentioned before, our final version utilizes computer vision, in this case Elite Motion. The collision detection runs in parallel for all fingers and hand joints, and so does the actuation of solenoids, which allows for fully independent control. We compared Wireality with other hand-centric haptic systems. Among the devices that provide collision feedback, for example, the VR haptic drones, while the method is innovative, it consumes 10 times the amount of power compared to Wireality. Another system that provides collision feedback is the claw, which uses servo motor and voice coil actuator. While it can simulate grip and texture, the weight of the system is equal to 40 Wireality modules. Wireality's use of a ratchet gear as the locking mechanism is also unique among these devices. Details of the table can be found in our paper. Our final implementation accomplished 3 key design goals: lightweight, low cost, and low power, important for future worn consumer uses. Furthermore, we evaluated our system performances through a series of tests. Minimizing latency is critical in rendering realistic haptic feedback. We measured our system's end-to-end latency, which was 29 milliseconds on average. The breakdown of the latency can be found in our paper. Maximizing freedom of the movement is crucial in creating an immersive VR interaction. Our system allows a range of motion with a radius of 83 centimeters from the wearer's shoulder, which we found to be sufficient to cover virtual objects over a wide range of distances and angles to the wearer. Convincing haptic feedback needs to be spatially accurate. We measured a stop point when the finger collided with a static virtual plane at different movement speeds. We found a Euclidean distance error of a standard deviation of 1.8 centimeters. Of course, the quality of haptic sensations is subjective, and thus we ran a supplemental qualitative study with 12 participants. 6 of our participants had no prior VR experience. We included 3 haptic conditions in our qualitative study. The first was bare hands. As an additional baseline, we included a controller condition with vibration feedback on the hand collision. Our third and final condition is Wireality, using our 7-string implementation worn on the right shoulder. In each haptic condition, participants interacted with 5 exemplary objects: a wall, a 45-degree tilted flat surface, a sphere, a pole, and an irregular object. After completing all objects in a condition, participants were asked 3 questions on a 7-point Likert scale. Specifically, the questions were: how realistic was the feeling of the object? How comfortable was the interaction? And how free was your movement? While we were disappointed that Wireality was rated significantly lower in terms of comfort and freedom of movement, it was not surprising. Compared to bare hands and a small handheld controller, our prototype is clearly more restrictive and less comfortable. That said, in this research, we focused our engineering efforts on achieving a new level of realism, which our results demonstrate. A commercial implementation would no doubt place greater emphasis on ergonomics. Now let's take a look at the applications of Wireality. Wireality could be used to enhance interactions with a range of virtual elements, including walls, boundaries, and other infrastructure. Large and heavy objects such as furniture, appliances, sculpture, and automobile. Interactors such as touchscreens, buttons, and levers, and even non-player characters. There are of course rooms for improvement and future work. Wireality's simulation of flat surfaces fails when a user translates their hand after touching a surface or object. The inability for a latch to be released without withdrawing one's hands also means user cannot explore complex geometries in a continuous forward motion, but rather requires pawing at objects. We suspect that visual haptic illusions, such as haptic retargeting, could be used to great effect to mitigate this limitation. Another limitation is the inability to simulate the grasping of smaller objects, like a pen or a coffee mug. Any geometry that involves the finger curling, such that there is no line of sight between the hand attachment and the corresponding haptic module, means the string will press against the skin, reducing realism by adding an unrelated sensation. Another force we cannot simulate is the massive handheld objects. This is again when we focus on large stationary objects that are placed on the ground and fixed obstacles, things that one does not pick up. Please see our paper for full technical details and discussion. Thank you for watching.